Hi everyone! Welcome to part 4 of chapter 16. Today we're going to continue our talk on weak acids and weak bases by applying them to salts. And in chemistry, salt just means ionic compound. So we're going to look at what ionic compounds do to the pH when you put them in water and they dissociate. So, like I said, salts are ionic compounds. And we've talked about before, sometimes it will make table salt, sodium chloride. Like if you mix hydrochloric acid and sodium hydroxide, you will get salt. But typically when we say the term salt, we're just talking about any ionic compound. And salts that are soluble will form ions in solution. That is, the ones that dissolve will float around as charged particles in solutions. So if we have the cation of a strong base or an anion of a strong acid, those don't ionize water, right? So those are not going to be strong enough to be able to pull a hydrogen off of water or donate hydrogen onto water or anything like that, right? So they will not affect the solution pH at all. However, if we have a cation of a weak base or an anion of a weak acid, those actually will ionize water and they will turn water into OH- or H3O+, and therefore it will affect the pH of the solution. So, for example, so this is sodium bicarbonate. Okay, we use that in lab. We use it to neutralize acids. But if we just put sodium bicarbonate in water, that will form a basic solution. So if we think about sodium bicarbonate, so sodium bicarbonate will break into Na+ and bicarbonate in water. Okay, sodium is the cation of a strong base, sodium hydroxide. And the way that I'm getting that, right, anytime you have a cation, right, it's positively charged, we're going to add on OH to see what that makes. And anytime you have an anion, right, that's negatively charged, we're going to add on a hydrogen and see what that makes. Okay, so anytime you have a positive charge, add on an OH. Anytime you have a negative charge, add on an H, just to see what these came from. So the fact that sodium here came from sodium hydroxide, which is a strong base, that is not going to affect the pH. Okay, so not affecting our pH. But bicarbonate came from a weak acid. It came from carbonic acid, which means that that anion can affect the pH. So since we have, right, our carbonic acid was a weak acid, this is the conjugate base of a weak acid, and therefore it is going to act like a base in solution. So our solutions of sodium bicarbonate are basic because they have this ion present. If we have anions, just any anions in general, they will form basic solutions like bicarbonate, or they will form neutral solutions if they came from a strong acid. And then if we have a cation, they will form acidic solutions or neutral solutions like this sodium did. Okay, so if we think of any anion, anything at all, you can think of that as a conjugate base of an acid, right? That's what I was talking about before. Like we had bicarbonate, and I said, okay, let's see what acid that came from. So if we add an acid, if we add a hydrogen onto it, okay, that came from carbonic acid. Or, say we had chlorine in solution. Okay, if we add a hydrogen onto that, that came from hydrochloric acid. So anytime we have an anion, we're going to add a hydrogen on just to see what acid it might have came from. So if it came from a weak acid, then this will cause a basic solution. If it came from a strong acid, then it will cause a neutral solution. Okay, but any anion theoretically could be a base. Like I said, these ones that come from the strong acid, though, are not going to be strong enough to ionize water. The stronger the acid, like hydrochloric acid, the stronger the acid, the weaker the conjugate base. So hydrochloric acid is a really strong acid, therefore chloride is a really weak base. However, carbonic acid is a weak acid, so its conjugate base is going to be stronger than chloride. Okay, like I said, any anion that came from the conjugate base of a strong acid is pH neutral. So like I said, this was coming from hydrochloric acid, which you're seeing over here. And any anion that's the conjugate base of a weak acid will be basic. So fluoride came from HF, right, which is a weak acid. Remember I told you that's the only binary acid of the halogens that is a weak acid. And so that will cause, right, that means F minus, right, our fluoride, can act as a weak base because it's the conjugate base of a weak acid. Okay, the opposite is also true. The stronger the base, the weaker the conjugate acid. So any cation that came from a strong base is pH neutral. So this would be like sodium, it came from sodium hydroxide. So anytime you have sodium in solution, it's going to be pH neutral. And any cation that's the conjugate acid of a weak base, though, is going to be weakly acidic. So here we have ammonium. And the way that we can figure out what ammonium came from is just to pull one of the hydrogens off. So, we had NH3 and it added onto a hydrogen to become NH4. So we can just pull one of those hydrogens back off to figure out what weak base it was. So anyways, anytime we have these conjugate acids of a weak base, they will cause an acidic solution. All right, so here it is, just kind of as a diagram. So as you can see up at the top, we have all of these strong acids up here. Okay, well, we don't really look at H3O+, but these strong acids here. And all of their conjugate bases on this side, those are all going to cause neutral solutions because, again, the stronger the acid, the weaker the conjugate base. And if we have a really strong base down here, right, their conjugate acids will, not affect the pH. They're going to be neutral as well. But all of these weak acids and weak base combinations in the middle, those are what can affect the pH. So if you have the conjugate acid of a weak base or the conjugate base of a weak acid, those can affect the pH, and they will act as acids or bases in solution. So since these are going to act as acids and bases, we need to figure out what their Ka and Kb values are. So a lot of times, our reference books, our textbooks will just give Ka values because you can find the Kb values from them. So it's a little bit redundant to list, okay, here's the Ka and here's the Kb. Even if it's a base, sometimes they'll still list the Ka just to be consistent. Okay, the reason for this is that we can solve for the for the Kb value from the Ka. So let's just take this one for example. So I'm using HA as any generic weak acid. Okay, so if our acid reacts with water, it's going to produce hydronium and the conjugate base. And here's our Ka expression. Okay, well, we know, like we were just talking about, this A- can act as a weak base in solution. So if we take our weak base here and we react it with water, right, it will produce hydroxide and a little bit of our weak acid again. Okay, so if we write our Kb value for that, right, then we have a Ka expression for our weak acid and a Kb expression for the conjugate base. Well, their net overall reaction here, that should look familiar. That's the dissociation of water, right? The autoionization of water. So the way that we are, when we add these reactions together to get this overall reaction, remember, how we manipulate Ks when we do that? We are going to multiply these Ks together. So adding our reactions together got us to multiply these Ks. So Ka times Kb, and if we, cancel out all of the stuff that appears on the top to the bottom, we're getting H3O plus times OH minus, which we know from before, that's Kw. So we can use Ka times Kb equals Kw, which is 1.0 times 10 to the minus 14, right? We can use that if we have Ka to solve for Kb, or if we have Kb, we can solve for Ka. Okay, so this is what you need. So we were just talking about, conjugate acids of weak bases and conjugate bases of weak acids can act as acids and bases in solution. But we can also have cations that are very, very small, highly charged metals. Those can affect the pH as well, and they will cause it to be weakly acidic. Okay, and here's how it works. So if we have, say, aluminum, right, that would be a very small, highly charged metal, right, because normally aluminum is 3+. So these cations are hydrated. Okay, and so for now, don't worry about how many waters there are on this aluminum. I'm not going to ask you to know that right now. Just I would give you this. Okay, but if you saw something like this, and this is called a complex ion, if you saw something like this, I would expect you to recognize that it's going to act as a weak acid. And I would expect you to be able to write the reaction for it. All it does though, right, this, since it's a weak acid, right, and acids are proton donors, right, so it will give away one of those hydrogens from these 6 water molecules to this, free water molecule. And so that will leave us 5 regular water molecules and 1 that has lost one of its hydrogens. And that changes the charge from a 3 plus to a 2 plus because we lost one of those hydrogens. And then this becomes H3O plus just like normal. Okay, so again, small, highly charged metals can do this. Alkali metals, right, the ones in the very first column like sodium and lithium and potassium, those only have a 1 plus. And they can't do this. And neither can the alkaline earth metals. They all have a 2 plus. They are not highly charged enough to do this. So any alkali metals or alkaline earth metals, they will always be pH neutral. But if you have something very small and highly charged like aluminum, then it can act as a weak acid when it's hydrated. Okay, we're going to go through a bunch of different salts and try and figure out whether they are acidic or basic or neutral. So if we have the cation from a strong base and the anion from a strong acid. So here's some examples. We have potassium chloride, potassium nitrate, sodium chloride, sodium nitrate, right? So these are coming from things like, the potassium is coming from potassium hydroxide. The chlorine's coming from hydrochloric acid. The nitrate is coming from nitric acid. What else do we have? Sodium from sodium hydroxide. And I think that's it, right? But those are all strong acids and strong bases. And since we have all of these strong acids and strong bases, right, both the ions are neutral. None of these cations or anions is from a weak acid or a weak base. And that's what we're looking for in order to change the pH. But since both the cation and the anion are from strong species, the whole pH is going to be neutral. Okay, so these salts, they're just going to dissociate in water. pH is neutral, nothing exciting happens. Just as like a pro tip, anything that's got sodium, potassium chloride, or nitrate, because you'll see those a lot, anything with any one of those 4 ions is not going to affect the pH because it came from a strong acid or a strong base. So if you see any one of those 4 ions, you can just ignore them. You don't need to figure out whether or not they, change the pH. All right, so now let's look at these ones. So here we have a cation from a strong base and an anion from a weak acid, right? Again, like I told you before, you can just kind of ignore sodium, potassium, sodium, right? But what we're left with is acetate and cyanide and fluoride. Okay, and all of those came from weak acids, right? Again, the way that you can figure out if it's a strong acid or a weak acid, just put a hydrogen on the front of that anion. So like acetate came from acetic acid, which is not one of the 7 strong acids you need to memorize. And then, cyanide came from hydrocyanic acid and fluoride came from hydrofluoric acid. All 3 of those are weak acids. So since they came from a weak acid, all of these are going to act like bases. And since we put, essentially we put a bunch of bases in solution, that will make it basic. Again, all of those cations came from strong bases, so they're not going to affect our pH, but all of the anions came from weak acids, so they are going to act as their conjugate bases and make it a basic solution, right? So all of these basic anions are strong enough, right, because they came from a weak acid, that makes them a strong enough base to be able to ionize water and turn it into hydroxide. And like I said before, ignore all the sodiums, potassiums, chlorides, and nitrates. All right, now we're going to look at the opposite. So the cation is coming from the weak base, and an anion is coming from the strong acid. Okay, so if we break these apart, right, we're going to get ammonium, right? We're going to ignore the chloride, and then this one also ammonium, and then again, ignore the nitrate. Okay, so ammonium, to figure out which, base that came from, we're going to pull one of the hydrogens off. That's leaving us with NH3. That's ammonia. And we know ammonia is a weak base Therefore, ammonium is going to act as a weak acid. Okay, so these cations are acidic because they are the conjugate acids of a weak base. Therefore, they're going to make the solution acidic. Both of the anions here, the chloride and the nitrate, are neutral because they came from strong acids. So since they came from strong acids, they are really, really, really weak bases, can't ionize water. So these acidic cations, right, these ammoniums, can act as a proton donor, and they can ionize water. So the ammonium will give up one of its hydrogens to water, and then we'll be left with ammonia, which is the base, and then the hydronium ion. And like I said, disregard any of those 4 ions. All right, now we have what I was talking about previously. We have the cation is a highly charged metal ion. So see here we have aluminum, right? And that's Al3+, and this is iron 3+, right? So both of those are small, highly charged. These anions came from strong acids, right? Nitric acid and hydrochloric acid, so we're going to ignore those. But the cations here are small and highly charged. So when we put them in water, they are going to become hydrated, and they will act as a weak acid, okay? And that will make our solution acidic. So again, they're going to become hydrated. I'm not going to expect you to know how many waters add on to it right now, but what I want you to know is that it will become hydrated and it will form what's called a complex ion. And a complex ion is a species that's got multiple different things together, and it has an overall charge. Kind of like a polyatomic ion, but they're held together a little differently. We're going to get into this more in a later chapter. And then that complex ion can act as an acid by ionizing water, right? It will donate one of its hydrogens to the water, and it will form the conjugate base in the hydronium ion. Since we have hydronium ion, that's acidic. So now, though, what happens if we have both, right? What if we have the conjugate acid from a weak base and the anion the anion is a conjugate base of a weak acid, right? Like if we break this first one, we're going to break this into ammonium and acetate. Okay, well, ammonium came from ammonia, which is a weak base, and acetate came from acetic acid, which is a weak acid. So both of those are weak, so both will affect the pH. Same thing down here, right? We have ammonium and cyanide, which came from ammonia and hydrocyanic acid. Again, both of those are weak, so they will both affect the pH. So then we need to go and figure out the Ka's and Kb values. So if the Ka for the acidic ion is greater than the Kb for the basic ion, then the solution's acidic, right? And that should make sense. Whichever one is going to, ionize water more. Remember that these Ka and Kb values are telling you how much water they will ionize, how much they will dissociate in water, okay? So the one that, ionizes water to a greater extent, then, that one wins. So like if we are going to produce more hydronium than hydroxide ions, it'll be acidic. But if the opposite is true, if we're going to produce more hydroxide ions than hydronium ions, then it will be basic. So you're going to need to figure out the Ka and Kb values if both of them come from weak species, okay? So if we have the, cation from a weak base and the anion from a weak acid, then we'll compare the Ka and Kb values, figure out which one's bigger, and then you'll be able to tell which one's acidic or basic. If it happens that they are equal, and every once in a while it will, if the Kb of the basic ion is totally equal to the Ka for the acidic ion, then it's neutral, because essentially the hydronium that's being produced is being canceled out by the hydroxide that's being produced. And so we're just going to have a neutral solution. So let's look at what this looks like. So if we have ammonium fluoride, so that is going to break into NH4 plus and F minus. So the ammonium came from ammonia, and the fluoride came from hydrofluoric acid. This is a weak base. This is a weak acid, which means that this will act as a weak acid and this will act as a weak base, so both will affect the pH. So we need to figure out the Ka and Kb values to compare them. So we can look up the Kb value of ammonia. Since ammonia is a base, it's reporting a Kb value. But because its conjugate acid is going to act like an acid, we need to figure out the Ka value for the weak acid. So the way that we'll do that, we'll use that Ka times Kb equals Kw. We'll rearrange it and plug stuff in, and we can get the Ka value for the ammonium cation. And then we'll do the same thing for hydrofluoric acid. It's going to have a Ka value because it's an acid, but we need the Kb value of the fluoride because that's the one that's acting as a base. So again, we can use Ka times Kb equals Kw, and then go ahead and solve for that and figure out our Kb. And then we'll compare them. So if we look, which one's bigger? This one's bigger. So since our Ka value for ammonium is bigger than the Kb value for the fluoride, our solution is going to be acidic because the acid, right, will affect the pH more than the base. All right, that's been a lot of information. I want you to go ahead and try this out. So I have 3 salts for you here, and I want you to predict whether the pH of each of the following salts when they're placed in water is going to be acidic, basic, or neutral. Okay, so pause here, figure that out, come back when you're ready. All right, let's go over this. So if we look at the first one, right, we can break those apart. If we look, so we have Na plus is going to come from our strong base, sodium hydroxide, but this will come from a weak acid. Right? Okay, so since we have our cation from a strong base, that is not going to affect the pH, but we have an anion from a weak acid. So since it's an anion from a weak acid, that is going to be a conjugate base, right? This is our acid, this is our conjugate base. And when we put that, that anion in solution, it can ionize water and produce hydroxide. Therefore, since it's producing hydroxide, it will cause a basic solution and it will raise that pH above 7. Let's try another one. So we have potassium and cyanide. So when we break that apart, our potassium's coming from potassium hydroxide and our cyanide's coming from cyanic acid. Okay, again, this is going to be a weak acid, so that means this is a conjugate base. Okay, so when we put that cyanide in solution, right, it's a conjugate base, it's going to react with water, it's going to ionize it and produce hydroxide because it's acting as a base. And since that reaction produces hydroxide, it will be basic and our pH will be above 7. Last one. So we have ammonium and nitrate. So when we ionize that, or when we put it in water, that's going to break it to ammonium and nitrate. So this came from ammonia, and this came from nitric acid. So nitric acid is a strong acid, which means we are not going to pay attention to our nitrate, but ammonia is a weak base, which means that, ammonia is a conjugate acid. So when we put that in water, it's going to act as an acid. So this is our conjugate acid. It will react with water, and it will produce the hydronium ion. And since it's producing hydronium ion, it will be acidic, and it will make that pH below 7. All right, one last topic for today. So we need to be able to figure out the exact pH. So we've been talking thus far about, it will be acidic or it will be basic. But today's lecture would just not be complete if we weren't going to do some ice tables. So that's what we're going to look at now. So in that last example problem, we decided that ammonium nitrate was going to be acidic and it will have the pH below 7. But how much below 7? That's what we want to figure out now. So our problem is find the pH of a 0.2 molar solution of ammonium nitrate. And I gave you the Kb value of ammonia there. So our first thing is to write our equation. What's happening? So we had ammonium nitrate, right? So that broke into ammonium and nitrate. Again, the nitrate came from nitric acid, which is a strong acid. So nitrate is going to be a very, very, very weak base. So we're just going to ignore it. But ammonium came from ammonia, which is a weak base, meaning that this will act as a weak acid in solution. So we're going to write our dissociation reaction with water. So we have ammonium reacting with water to produce ammonia and the hydronium ion. And I have my Kb value over here. So we'll go ahead, we'll make our ice table. It said in the problem that was 0.2 molar. We're just going to ignore water, and then we have 0 of both of the other ones because we're going to go ahead and ionize. So when we react with water, we're going to do minus x, plus x, and then 0.2 minus x, x. Nothing exciting here. The only thing people do wrong, like up to here, is that they can't figure out whether, this is going to act as an acid or a base. So make sure you're paying attention to that. If it's positively charged, it's going to act like an acid. If it's negatively charged, it's going to act like a base. All right, so now this is producing hydronium ion in solution, which means it's acting like an acid. But we were given a Kb value. But we don't need the Kb value because it's not acting like a base. So we need to figure out the Ka value. So we'll use Ka times Kb equals Kw, and we'll rearrange and we'll solve for Ka. So now we have our Ka value, and we can go ahead and start solving this equilibrium. K is very, very small, so we can use the approximation, right? This is like really small, so we can definitely use the approximation. So if we go ahead and plug things in, we'll have ammonia times the hydronium over ammonium. And so we have our x times x, 0.200 minus x. We can go ahead, we'll use that approximation, right? And we'll get rid of that x there. So we have our Ka value is going to equal x squared over 0.2. And we'll just go through and solve, right? We'll multiply both sides by 0.2. We'll take the square root, and then that will get us the concentration of our hydronium ion. Then we can go ahead and find the pH by taking the negative log of that hydronium ion. And that's it. You'll notice though that this pH is not very low, right? Our ammonia was a weak base, but it was a fairly strong weak base, right? Times 10 to the minus 5 isn't bad. So it was a fairly strong weak base. Remember, the stronger the base, the weaker the conjugate acid. So yes, this ammonium does act like an acid in solution, but it's not a very good acid. So we're only getting a pH of about 5, which isn't very low, but it's still below 7, is still definitely acting like an acid. And that's it for today. So today we talked about how to recognize whether a salt would act like an acid or a base, or if it would just make a pH neutral solution. We also talked about hydrated, small, highly charged cations acting like weak acids. And then finally, we looked at an example problem of how, a salt can affect the pH, and we can actually go through and calculate the actual pH of the solution. In the chapter lecture worksheets, there are a ton of practice problems with these salts. I have found that most people can do the Ka problems for the weak acids. They can do the Kb problems for the weak bases. They're good at calculating, the pH of the strong acids and the strong bases. But the salts is where people trip up. Because when we start throwing salts in solution, we need to figure out what they dissociate into when you put them into water. And then what's going to affect the pH? Is the cation? Is it the anion? Will neither of them? Will both of them? Right? And those are the parts that are tricky. So you have a ton of practice problems on these in your chapter lecture worksheet. So make sure to check those out. Do as many of them as you can so you get really confident at them. And as always, if you have any questions about the lecture or about the problems in the worksheet, please send them my way and I will be happy to help you. Otherwise, keep working hard, and I will talk to you guys next time.